fork counter mode variants. Counter mode variants based on a generalized fork cipher. This is a work of Amit Singh Bhati, Elena Andreeva, Damian Vizag, and Bart Praneel, and Amit will give the talk. Based on a generalized fork cipher. This is a work of Amit Singh Bhati.
Hello, everyone. Thank you, Bart, for the introduction.
It should work. Is it there? No. No?
Yes. Okay. Perfect. So the contribution of this work is twofold. First, we define a multi-fork cipher, which is a generalization of the fork cipher, and it allows us to design and analyze generic modes irrespective of the underlying tweakable primitive, which can be a tweakable block cipher or fork cipher or any higher multi-fork cipher with branches greater than 2. So a multi-fork cipher is generalization of fork cipher in terms of in number of outputs. So a fork cipher, as you can see here, takes an n-bit block input and gives 2 n-bit as output. Multi-fork cipher generalizes it with the parameter s, as it gives as many output blocks. The security of multi-fork cipher is defined by its indistinguishability from s tuple of random permutations. Let us now take a look at generic counter mode, the major contribution of this work. So it's a counter mode based on multi-fork cipher. It looks like this. So it takes 2 input sequences, x and t, which is being fed to the underlying component called TCTR, the tweakable CTR framework. And it generates a key stream V, which is then XOR with the message like a counter mode to generate the ciphertext. If we zoom inside the TCTR framework, we see this is how it looks like. It consists of multiple parallel multi-fork cipher calls, and this is how the input and tweak sequences are used as input and tweaks to the underlying multi-fork ciphers to generate the key stream. If we simplify this, this is how the generic counter mode looks like, and here are the additional inputs and outputs. So this is the nonce, and R is some internal randomness, which if is used, then it should also be put as the output. So we get x and t as a function of these 3 variables, nonce n, randomness R, and a counter j. We define some simple rules to define these functions fx and ft. And these rules are as simple as in to get the efficient GCTR variance, which we call the simple GCTR variance. So there are 2 rules. The first one says that these fx and ft functions can be either a concatenation or an XOR of any 2 of these 3 variables, or it can be a copy of them. And it can also be a constant function independent of these variables. And the second rule says if fx, let's say, has already one of these variables, then ft should not have the same. So with these 2 simple rules, we get total 36 GCTR variants. And these 36 variants include the traditional counter modes and the counter and tweak mode. Let us now take a look at the security analysis results of GCTR. So the security analysis of GCTR is then using the abstraction of TCTR. And since the abstraction of TCTR is generic, the proof is generic, and in a single proof, we capture all 36 GCTR modes. For the proof, we have used a coefficient technique, and the results are as follows. So 18 out of these 36 GCTR variants are insecure, and the remaining gives you at least birthday-bound security under the notion of security. These 18 secure variants includes 3 beyond birthday-bound secure GCTR variants that are GCTR 1, 3, and 7. So from this analysis, our best pick is GCTR 7 and GCTR 3 in terms of security. GCTR 7 is best against nonce-respecting adversaries and also for certain restriction against nonce-misusing adversaries, whereas GCTR 3 is best for general nonce-misuse setting. Counter and tweak mode, which was proposed by Perrin and Shurin in Crypto 2016, reside inside the GCTR 3 variant of our GCTR analysis. So when it is instantiated with tweakable block cipher, that is the multi-fork cipher is instantiated with s equal to 1, we get the counter and tweak mode. But our generic proof provides a security bound for GCTR 3 that improves over the existing bound of counter and tweak mode. In particular, the bound security bound degradation improves from being in order of sigma squared to order of q sigma. It says that the counter and tweak mode provides better security when the average message length is longer. As a consequence of our security analysis, we have also revisited existing work that uses a counterline component. It's a THCTR, which is an encipheling scheme, and it uses GCTR4-like component internally. But the scheme has been claimed to provide beyond birthday-bound security, and GCTR4 in our analysis has been shown to provide only birthday-bound security. So we investigated this inconsistency and realized that the claims are incorrect. We show a birthday-bound attack and also point to the exact flaw in the security proof of THCTR. And an easy fix for this could be replacing the GCTR4-like component with GCTR3 or GCTR7 to get the claim beyond birthday-bound security. Okay, and since MFC itself brings speed up in efficiency, so it is expected to see if the mode also carry over the efficiency gain, and it's true for GCTR. So we analyze GCTR over MFC with instantiation S equal to 2, which is a fork cipher. In particular, we use fork skinny with GCTR and compare it with counter and counter and tweak modes, instantiated with tweakable block cipher skinny. And as you can see here, GCTR performs better than the other modes. In numbers, GCTR provides at least 20% speed up than the other two modes when instantiated with fork skinny against skinny. So the real summary is as follows. We define a generic counter mode over the abstraction of multi-fork cipher, which provides all desired properties of counter mode with some extra features in terms of security and efficiency. So for security, we get security against nonce misuse, nonce misusing adversary, and birthday-bound security, and also in some cases full and bit security. And in terms of efficiency, we get at least 20% speed up when the multi-fork cipher is instantiated with fork skinny for GCTR and compared with counter and tweak mode with skinny. I quickly will tell about the use cases of GCTR in practice. There are various use cases when put in groups. Two major groups can be defined like this. The first one would be applications that requires only encryption and nonce misuse resistance is desirable there. And second is as GCTR as a building block inside some large crypto system that tries to achieve something larger. So an example could be, as we saw before, THCTR like an encipheling schemes or AAD schemes that are based on a synthetic IV kind of structure, SCT or encrypted MAC. Okay, and this is the last slide. So I will talk about some open problems that are left open by this work. The first one would be the obvious one, to design new secure and efficient fork cipher and multi-fork cipher with branches at least 2. And the second one is to design novel fork cipher and multi-fork cipher based modes that are not limited to encryption and can be used in various other security settings like Max or random generation or other privacy preserving applications. Thank you.
Okay, thanks, Amit, for the presentation. Are there any questions from the audience here?
So, Bart, may I ask the question?
Yes, you're Mridul, right? Who is asking the question?
Yeah.
Yes, go ahead.
So, Amit, nice presentation. By the way, in your construction, that you have this for the generalized counter mode, GCTR mode, you have instantiated with, say, this multi-fork cipher, and the parameter is like S. So what if I instantiate the same construction using the independent tweakable block ciphers, for example, say skinny instead of fork cipher? So how is it different from your construction?
Avijit, could you repeat the question?
Last part.
The last part.
Instantiated with what? With
with tweakable block cipher. Let's say for example, skinny.
As many tweakable block cipher, you mean, right?
Yes.
Yeah, it could be possible. So that's what the security notion of MFC captures. So you will get the similar bounds or exactly the same bounds, but the gain would be then in terms of efficiency, because then you have to make as many tweakable block cipher calls there, but here you making one MFC call, which could give you speed up.
Yeah, I understand, but if you instantiate or if you construct the fork cipher using, say, lower level primitives, then also you need to call the underlying primitives. Say, for example, if you want to instantiate your fork cipher using public permutation, then also, I mean, as per the recent constructions that we have seen, that I mean, you understand the question, right?
True.
But again, that you have to. Yes.
That's a specific case, right? That's a specific case to generate or to design a multifork cipher, which is the worst that you can design with as many permutations called in parallel. But it could be possible to design it, for example, like fork skinny, where you can save some number of rounds.
Okay. 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 I understand. Thank you. Thank you.
Okay. Any other questions? So no other questions here. Also not in the chat, I think. So if that's not the case, no. Okay, let's thank Amit again. One second. Hey, Christina, I do need your help. I'm sorry. I'm not used to this computer. Because if I want to share, indeed, yes, you get the old one, yes, so you have to close it. Yeah, that's what it was. No? Yeah, it's not here anymore. No, this is the old one. Yeah, this is the new one. Okay, so we just close this one and then go again. Ah, yes. This is no. Now you have to open. What is he sharing now? I don't know. Yes, just close. Close. Oh, yes, that's it. Yes, okay. That's the one. Yes, then a view. No, it was sharing now. No, it was not sharing. Yeah, it was sharing. This is sharing. This is sharing. Yes, view, full screen. Sure. Yeah, look at this. That's sure. Okay. Now you have to do it. Okay, the next talk is forking tweakable Evan-Mansour ciphers. It's a work by Wikyum Kim, Youngming Lee, and Joyoung Lee. And Wikyum will give the presentation.
Hello, my name is Wikyum Kim, and I will start my presentation. Authenticated encryption with associated data. AEAD can make all symmetric crypto functions. If you want Mac, you can make input as associated data and get tag. If you want encryption, you can make a message as an input and get ciphertext. If you want authenticated encryption, you can make message as input and get ciphertext and tag. That means if you can make AEAD, you don't have to concentrate that the primitive should block cipher. So there are some trials to make other primitives. Fork cipher is some new primitive for the AEAD. Fork cipher is expansion of tweak or block cipher. This is tweak. So fork cipher has one input but two output, and with tweak, designed for AEAD. PAEF mode is a kind of that. It has also associated data input and message input, then ciphertext output and tag. My contribution is the first probable security model for fork cipher, and suggested the most simple fork cipher, FTEM. FTM means forked tweakable evenmancer, and proved that FTEM has 2 and 3rd bit security. That means forking do not degrade the security. This is how I constructed fork cipher, FTEM. This is 2-round evenmancer construction. If you think the masking key and permutation, then masking key is 1-round evenmancer. A 2-round evenmancer can be thought as concatenation of 1-round evenmancer. And then tweakable evenmancer is the changes the key to the tweak key. then it is natural way to think two-round forked even answer should be like this. One round even answer after that, and forked, and one round even answer. You made FTEM construction, but in Provable security, the corresponding ideal oracle should be constructed to be proved. We think as this tilde means tree cover, and tilde Q and tilde R means tree cover permutation as an ideal. It is popular primitive for tree-cover block cipher ideal oracle. We think with that FTEM's corresponding ideal world construction is two concatenated tree-cover block cipher, and we got total security 2 and 3rd bit security. This below is 2-round even answer, and it also has 2 and 3rd bit security. That means tweaking did not degrade the security, and also fork did not degrade the security. And conclusion is this: fork cipher is a cipher that has 1 input and 2 outputs, and efficient in short message. Fork tree cover even answer is the most simple model of fork cipher, and two-round FTEM has 2 and 3rd bit security. And also it is same order of security with 2-round even answer. And there can be some future works that extend the round of fork or multi-fork, and you can think as it's multi-user security also. This is my presentation over.
Okay, thanks, Guillaume. Any questions from the audience? Okay, from online, there is one question in the chat. I'm going to ask the question. It's from Avijit. If we add more permutations in both the upper and lower layer, can we prove its security up to 2 to the 3n over 4? So I think the question is, you have one permutation call, and then you fork, and then you don't do 1 but 2 permutation calls. What do you expect?
Yes.
It is. I think it is extending the fork round. Yes. I think there can be some. Advance in Provable security, but I know that 4-round tree-cover even answer, 3-round and 4-round tree-cover even answer has not proved yet. So I think it will be some hard question.
We know that R-round even Masu cipher is optimally secure. At least asymptotically secure, right? So in that way, if I just fork it for one more round, then can we prove its security up to 2 raised to 3n by 4?
Avijit, was that a question or a remark?
No, it's a question. Like we know this, right? From the general result.
Yes.
Oh, okay, maybe we can.
Yes. Let's take that question offline then.
Yeah, sure.
Are there any other questions? Okay, if there are no other questions, let's thank Guillaume again. And now we're going to two online talks. Yes, okay, there we are. Could you full screen? Yes, great. I will try to, I cannot minimize this.
So the third talk of this session is provably quantum secure tweakable block ciphers. It's the work of Akinori, Jose Yamada, and Tetsu Iwata, and Akinori will give the presentation.
Thank you for introduction. Can you hear me? Can you hear me?
Yes, we can hear you, Akinori.
Okay, thank you. Then let me start. So thank you for the introduction. And this is the result of our paper. In Crypto 2016, Kaplan et al. Showed that some TBC modes of block ciphers, such as LRW, are broken by polynomial time quantum query attacks. And there has been no TBC modes proven to be secure against quantum query attacks. And in our paper, we showed a new construction, which we name LRW2. This is a TBC mode of block ciphers with provable security against quantum query attacks. And next, I would like to explain the background of our research. So first, this is the usual classical attack model of chosen plain text attacks. There is an adversary with classical computer, and an encryption oracle is given to the adversary. And next, in the quantum setting, we can consider two attack models, Q1 and Q2. In the first model, Q1, the computer of the adversary is replaced with a quantum computer, but the encryption oracle is the same as the classical oracle. On the other hand, in the Q2 model, the oracle is also replaced with a quantum oracle. And now the adversary can make queries in quantum superposition. And the response from oracle is also in quantum superposition. And our focus is the Q2 model. And next, I'd like to explain the basics of LRW constructions. The constructions are the most basic mode of BCs for TBCs introduced by Liskov, Rivest, and Wagner. And there are two variants, LRW1 and LRW2. So both of them are proven to be secure in the classical setting. But unfortunately, they are broken in polynomial time in Q2 model. And so far, there does not exist any TBC mode with provable security against Q2 attacks or quantum query attacks. And so this is the starting point of our research. The goal of our paper is to realize a TBC mode with provable security against quantum query attacks. And next, I would like to introduce our new construction, LRW2. So please recall that LRW1 looks like this. This is broken in Q2. And this structure has this property. A t-dependent value ek of m is directly added with a variable t under full control of adversaries. So very roughly speaking, this property is the reason that LRW1 is completely broken in the Q2 model. And so to break this property, we introduce another block cipher code here. And this is our new construction, LRW2. And we showed this theorem. LRW2 is indistinguishable from tweakable random permutation, or ideally random tweakable block cipher, by Q2 attacks up to order 2 to the power n/6 quantum encryption queries. And we assume adversaries can query both of M and T in quantum superposition. And we used the compressed oracle technique by Chandler to prove the theorem. So roughly speaking, history of queries to random functions can be recorded even in the quantum setting by using this technique. And thanks to this technique, we can use the classical intuition of lazy sampling to some extent. And next, I'd like to provide a very rough overview about our proof. So the technically hardest part in our proof is to show indistinguishability between this function and this function. And roughly speaking, when we use the compressed oracle technique, database or history of query is kept by the oracle. And so the oracle for this RF0, RF1, RF2, and RF these are distinct and independent random functions. And the oracle of this function maintains 3 databases, D0 for RF0, D1 for RF1, and D2 for RF2. And roughly speaking, we say that this database is good if it does not contain collision here. And similarly, we say that a database or history of query for this function is good if it does not contain collision here. And roughly speaking, there is a natural one-to-one correspondence between the set of good database for this function and the good database for this function. And this correspondence means that the two functions are indistinguishable as long as databases are good. And this further means that what is remained to be shown is producing a bad database or non-good database is hard. That is, producing a kind of collision is hard. And we can indeed show this claim even in the quantum setting, thanks to the compressed oracle technique. And next, I'd like to provide some remarks. Unfortunately, our construction is not secure against chosen ciphertext attacks, even in the classical setting. And secondly, very recently, we found some detailed errors in the details of the proof. And we observed that they can be fixed by modifying details without changing the final bound. And we are preparing an errata, and we are going to make it public soon. And finally, I'd like to summarize today's my talk. So in our paper, we showed a new construction, LRW2, with quantum provable security against quantum Q2 attacks. And unfortunately, so very recently, we observed some errors in the details of the proof, but we observed they can be fixed without changing the final bound. And an important future work is to construct construction with security against the quantum chosen ciphertext attack, because ours is not secure against chosen ciphertext attack. But to prove security against chosen ciphertext attacks, a permutation version of the compressed oracle is necessary. And I think this is a somewhat difficult task, but still they are important and interesting future works. That's all. Thank you for your attention.
Okay, any questions from the audience? I'm not muted. No, I'm not muted. I need to. Zoom is not muted. Not anymore. Yes. Thanks for yes. Is it a long question or a short one?
Short one.
Yeah, then I can repeat it if you want.
Yes, so I just wanted to ask something about your proof technique of recording oracle with errors. So do you somehow prove that it's indistinguishable from the standard oracle? Because I think, as far as I remember, Zonde proves that. But do you think it's important to prove that it's indistinguishable from the standard oracle?
Yes. So Ritam asked a question about the proof technique.
Yes.
Do you prove it indistinguishable from the standard oracle? Because Zandi proves it in his compressed technique, I think. And his question is about your proof technique. How did you approach this?
Excuse me, but I didn't get what is the question.
Okay, maybe just come here anyway. I'm sorry. So Rita will ask the question himself.
Yes, please.
Okay. Hi, Akinari. My question is that you're recording standard oracle with errors. So do you prove somewhere that it's indistinguishable from the standard oracle, or do you think such a proof is important, or just that's my question?
You mean our oracle? Okay, your question is whether our oracle is indistinguishable from standard oracle by Chandri.
Yes, exactly.
Yes, I think they are indistinguishable completely. Yes.
Okay, thank you, he says. Any other question? I actually also had one question, basically two related, but so you use 3 primitive calls, and you get, classically, it's only birthday bound secure. So from a classic perspective, it's not a very efficient scheme. With three block cipher calls, you can even get beyond birthday bound security.
Yes.
Do you think you can get with 3 block cipher calls then a better scheme that even achieves better security? Did you explore these possibilities?
I think yes. Yeah, I think it would be theoretically possible to achieve such security, but I think the problem is proof technique. I mean, the compressed oracle technique is not applicable currently, not applicable for permutations, and I think some innovation on the proof technique will be necessary to prove such a thing.
Okay, thanks. If there are no other questions, yes, let's thank Akinori again.
Thank you.
And then we go to the next talk, which is also online. Ike. Please share the screen. Yes, we see your screen. We just see a black screen you're streaming now. Yeah. You're just streaming a black screen now. Is that correct? And you're muted. And now, yes.
Finding the correct one. I see.
Okay, so we go to the fourth talk of this session. Is highly secure Nonspace Max from the sum of tweakable Evan-Mansurs, tweakable block ciphers. It's a work by Wong-Sok Chai, Akiko Inoue, Byung-Hak Lee, Joyoung Lee, Ike Lis, Kazumi Matsu, and Yusuke Naito. And Ike will give the presentation.
Thank you. Can you hear me? Is this working?
No, not very well.
It's quite soft.
Then I try to speak a little louder. Is this better?
Yes.
Yes, that's better.
Thank you very much. And thank you for the introduction. Clearly, as all of you know, there are a few desired of message authentication codes. They shall provide everything from high efficiency to high security, and if possible, they should even be robust if you mistake to use your nonces only once as desired. And as you probably also all know, tweakable block ciphers are extremely useful to fulfill all these goals simultaneously. If you have only small tweaks, so you can process a domain and have more elegant and more simple proofs. If the tweaks are larger, in the order of like this block size, you can process more input material and be more efficient, or you can take the nonce and increase the security of your construction. And in this direction, Koyati, Lee, and Soron at TOS 2017 proposed 4 elegant Mac designs from universal hashing and a block cipher call. 2 of them were tweakable block cipher based, nonces tweak and hashes tweak as shown here. The first one ensured n-bit security and a graceful degradation when nonces repeated too often. And the second one had the improvement that it's stateless deterministic, so did not need any nonces, and had n plus t half-bit security ignorant if there are nonces or not. But on the other hand, could not benefit if nonces were available. The research questions that ignited this work were, how can we strengthen these interesting designs with, if possible, minimal changes? For the first one, for nonces tweak, how can we increase the security when nonces may repeat often? And for the second one, can we achieve optimal security even if there are nonces in the game? And we ended up with 2 contributions, with 2 constructions that we called NAT2 and extended hashes tweak. Both profited from the sum of independent tweakable block ciphers. At the beginning, we had some observations which design components we had or we should be using. For example, the sum of independent PRPs. Well, this construction, as we know, is n-bit or can achieve n-bit security, and we are limited anyhow at the n-bit bound, since the adversary can simply guess the tag, and if you have an n-bit tag, so the security cannot be extended beyond this v by 2 to the n. When nonces are respected, we would like to have full security, as the nonces tweak construction already has, so the nonce should be in the tweak. And if they collide, we would have a collision at the birthday bound, so we would need 2 n-bit hashes under the assumption we have an n-bit hash function. And we would need to process n, I forgot it in the picture, we had to process n and m in the hash function. Moreover, when we have tweak sizes at most of the block size, we would need 2 tweakable block cipher calls anyway to process the hash and the nonce. So with these design principles, we landed at our 2 constructions. NAT2 is the sum of 2 nonces tweak instances, which preserves n-bit security on the nonces and falls back to the sum of independent PRP security when nonces will repeat. How does this look then in bounds? So when we have no nonce repetitions at all, we preserve the original bounds of Kolyati et al.'s construction. So we are limited only by the number of verification queries. So when we have as many verification queries as we have MAC queries, we have our previous n-bit. And we have the old bound also when we have less here square root of q verification queries, so it gets better then. However, when nonces get misused, while the original constructions were still nice, so to say, at about 2n by 3 queries, at about 2n by 3 security, we still land at n-bit security, and if we have even less verification queries, we get still better with that. In the case that all Mac queries use the same nonce, we still land at about 2n by 3, versus the old one was n by 2 security. And if we have when we have fewer verification queries of the order of square root of q, we even could prove about 3n by 4 bit security for that. The second construction is called extended hashes tweak. It extends the original design by having this sum of independent permutations where we possess the nonce in a second tweakable block cipher call with an independent key. And here it's the other way around. Here, when there are no nonces respected, we end up at the same security bounds of n-bit security as before. However, when we are nonce respecting, our bounds get better in theory, and we are limited only by the number of verification queries. So when we have a lot of them, we still end up at the n-bit bound, but we improve over hash as tweak when there are fewer verification queries. In terms of, yeah, we need more operations than the original constructions. However, we argue that the additional computations that we introduce are minimal. This means we add another tweakable block cipher call that is independent from the first one. However, this may be also parallel. We have to process the nonce in both functions in terms of enhanced hashes tweak. This is an additional effort for the hash function, and we see we have an additional hash function call for nonces tweak too. Yet we argue that those are minimal from our observations to obtain these higher security bounds. In sum, we propose two highly secure non-spaced tweakable block cipher-based Mac designs with minimal changes from the original designs hashes, nonces tweak and hashes tweak by Coyote et al. With higher security even when the tweak size exceeds the block size. For our first design, we stay at n-bit when we keep up with nonces. However, when nonces repeat, often we have at least 2n by 3 bit security, and if we have fewer verification queries, we can even exceed that. For extended hashes tweak, we always will have this n-bit security even, but we can get better if nonces are respected for that. Future work could involve mixed constructions that we had started, or a security analysis in the ideal cipher model. So far on this, and looking forward to your question.
Okay, thank you. Any question from the audience? Okay, any question online? Okay, I actually had a question. I had two questions, by the way. So one is on this nonce as tweak 2 approach. How did you approach the proof? Is it just a black box combination of the sum of permutations with NAT, or did you have to prove it from scratch?
No, this was a dedicated extension of the mirror theory to get beyond even this 2n by 3 bound. So this was also an extension of earlier results, I think, by Kim et al. From Eurocrypt 20 and maybe also by Data et al. No, this had to follow a new path of defining nice graphs, nice transcript graphs, and then using a bound on their solutions for the final proof. Unfortunately, not so easy.
Okay, let me ask one more quick question, because you kind of have graceful degradation in your proof. So you have the case with the nonce-respecting setting, the case where you have, I think, square root of q nonce-repetitious. Is the bound actually a function of the number of nonce misuses in this, in terms of the original definition of this nonce degradation security? I think of Avijit et al.
It should be, but there are more terms. There are a lot of terms, so I don't have the complete bounds.
So what I mean here is that you actually have three cases where mu is 0, where mu is square root of q, and where mu is q. Do you prove it for arbitrary mu, or just for these three?
Yes. This is not a case. This is just for illustration.
Okay, thank you. If there are any other questions? If not, let's thank Ike again. Then we have I have to do some magic. 1 second. Wait, wait. Yes, there's the magic. Because we closed that one.
We close them all? Not here?
Ooh. Ethan, it's there. Yes, it's still there. Great. Yes, this one's shared. Yes, but this works. This is the correct one, I think. No. Yes. Yes, this is the one. Yes. The other one we closed. Yes, and yes.
Okay, and the next talk is CTet Plus, a beyond birthday bound secure tweakable and ciphering scheme using a single pseudo-random permutation. It's a work of Benoit Colliati, Jordan Eaton, Virginie Lallemand, Byung-Hak Lee, Joyoung Lee, and Marine Meunier, and Jordan will give the presentation.
Thank you. Thank you for the introduction. So in this work, we're interested in the full disk encryption problem. In this context, we want to encrypt data that is divided into sectors of a few hundred bytes to a few kilobytes. The problem that we have is that there is no room to store additional data, like a nonce, random IVs, or even an authentication tag. In order to work around this limitation, we'll have to encrypt each sector independently. The current standard of disk encryption is called AES XTS. It is a tweakable mode of operation combined with the XEX transformation for AES. Note that the XEX construction is secure up to the birthday bound, which means that this construction is secure as long as the number of queried blocks is small in front of 2 to the 64. In this construction, we identify two problems. The first one is a small granularity, while the second one is that big data centers most likely hold at least 2 to the 50 bytes, which is close to the birthday bound of 2 to the 64. In order to solve the granularity problem, we'll use wide tweakable block ciphers that use all sectors as input blocks, even if they are based on a tweakable block cipher or block cipher with small domain size. Using such an algorithm, 1 bit change in M1 will affect all ciphertext blocks, unlike the previous construction where it only affected C1. Several such examples already exist, and they can be divided into 3 families: the encrypt mixed encrypt, the hash encrypt hash, and the hash counter hash. All these constructions require roughly 2 AES calls, or 1 AES call and 2 field multiplication, and they are secure up to 2 to the 64 queries. However, these constructions are not, do not solve the birthday bound problem, which means that if we want to achieve behind birthday bound security, we'll have to increase the number of layers, the linear layers. So the 2-round SPN has already been seen as a tweakable domain extender for block ciphers, and it can be seen as an hash encrypt hash paradigm, and is secure up to 2 to the 2n divided by 3 queries, as long as T and T-1 satisfy some property that was introduced in crypto 2018, which namely means that they are almost super blockwise universal and uniform, a property that we shorten into SBU. Our first contribution in this work is to introduce the CTet plus construction, which is an optimization of the 2-round SPN that uses the same permutation for the nonlinear layers and uses a more efficient middle layer that replaces 1 field multiplication per block with 1 doubling per block. And it is secure up to 2 to the 2n divided by 3 queries as long as T and T-1 are SBU. Additionally, we introduce an instantiation of the CTet plus construction using a round reduced AES of 6 rounds. Overall, our construction uses 1 tweak of 128 bits, 1 white block of 128 W bit words, and relies on 6 keys of 128 bits, 2 for each of the T linear layer, 1 for the L linear layer, and 1 for the reduced round of AES of 6 rounds as S-box. Our security analysis allows us to claim 127 bits of security. So in our analysis, we rely on 2 complementary arguments. The first one is a generic security proof that justifies the fact that the generic structure of AES6 CTet plus is sound and will resist attacks with high probability. This proof relies on the H coefficient technique. Moreover, we provide a dedicated crypto analysis to justify why our instance with a 6 round of AES is still secure. In our crypto analysis part, we concentrate on 2 attack directions. The first one is to exploit weakness of AES and extend it to the full construction, while the second one is to use structural attacks like yo-yo attack and tourniqueted differentials. To conclude this talk, I would like to quickly compare our construction with previous one and talk a bit about our implementation. So as far as the generic security bounds are concerned, only 2 constructions achieve beyond birthday bound security, our construction CTet plus and the tweakable 2-round SPN. As you can see, our construction is 0.4, roughly 0.4 cycles per byte faster. And this improvement mainly comes from the replacement of the middle layer to a simpler one. Thank you for your attention.
Okay, thanks for your presentation. Are there any questions? So here, I hear something online. Is that correct?
Bart, can I ask a question?
Yes, Avijit, go ahead.
Yes. Hi, Jordan. So do you prove your construction in a random permutation model or in standard model? Have I made myself clear? So do you make this SBox secret or are you giving the access to the adversary?
No, the SBox is secret.
So, okay, so SBox is secret and you instantiate this SBox with AES6, right?
Yeah.
But I suppose that AES6 is available in public. I mean, anyone can evaluate AES6.
Yeah.
So in that model, I think it would be better that if you have proven your construction in random permutation model. I mean, that would fit the instantiation, I think.
Okay, thank you.
Okay, any other questions?
Okay, I actually have one.
Yes, go ahead, Tetsu.
Okay, so you claimed 127-bit security for AES6 instantiation instead of 128. And why do you claim 127-bit security?
So 2 of the keys that we use do not have 128 bit of entropy. So you can't, I don't think you can claim that.
Okay. I have one more question. This is not relevant in the context of disk sector encryption, but the title says that this is an enciphering scheme. So I assume that you can handle variable length inputs. And do you have any comment on that? When the input lengths can vary, do you expect an attack, or this is not covered in the proof, or?
Well, we expect W to be quite big, so this would work on very large input, but we didn't think about variable input. No.
Okay, you mean, do you have an attack, or it doesn't cover it in the proof?
No, I don't think we have an attack.
Okay, thank you.
Okay, if there are no other questions, let's thank Ethan again. And yes. Yes, the other file is closed, so we have to open it. No, it's Ashwin, yes.
Okay.
Yes, and then share it. Yes, thank you. All right. And the last talk of the session is on length-independent security bounds for the PMAC family. It's a work by Bishwajit Chakraborty, Soumya Chattopadhyay, Ashwin Shah, and Mridul Nandi. And Ashwin will give the presentation.
Thanks for the introduction. as the title says, this talk is about the PMAC family. So let's start with the description of the simplified PMAC proposed by Ghazi et al. So this is just a block cipher based mode of operation for message authentication code. It's a parallelizable mode which takes a message M and divides it into n-bit blocks, and then masks the first L-1 blocks with a masking function, and encrypts them and XORs all the outputs to create a hash value, which goes as input to this EK prime, and the output is the final tag value. And when we substitute different values for K and or when we use different relations for K prime and L, we get different instantiations of SPMAC. Like PMAC, the original construction is achieved when you get when you set K equals K prime and L equals the encryption of 0, and tau is defined as the gamma I into L, where gamma is the gray code sequence. Similarly, we have PMAC 1, which is another instance with a simple change in the masking function, where you use powering of sequence. So you use a primitive element of GF2 to the n to create the masking values. In 2019, NITO proposed another variant called NPMAC, or we call it NPMAC, which is again a variant of PMAC 1. It uses two different powering up values. So, and the next part is the length independent PRF security. So what do we mean by length independent PRF security? So basically, we have the PRF guessing game. So the adversary tries to guess between a uniform random function gamma 0 or the real construction gamma 1. And you have this definition of the advantage. And length independence simply means that this advantage term should be independent of the message length. So our first contribution in the paper is a demonstration of a flaw in the analysis of NITO's variant of PMAC. To simply describe the flaw, we just consider this system of two equations in L1 and L2 over GF2 to the n, with this condition that at least 3 of the 4 variables A, B, C, D are distinct. 4 values A, B, C, D are distinct. So in the paper, NITO claims that the two equations are linearly independent, given that we have this condition that A, B, C, and D are distinct. And he argues it as follows. So he says that if the two equations are dependent, then you must have alpha plus beta equals gamma plus delta, and alpha cube plus beta cube equals gamma cube plus delta cube. And basically, if you just do some algebraic simplification after this, you will arrive at a contradiction that A equals B equals C equals D, which clearly contradicts the assumption that A, B, at least 3 of them should be distinct. But as you can see, the actual criteria for dependence is that alpha plus beta should be equal to C2 divided by C1 times gamma plus delta, and alpha cube plus beta cube should be equal to C2 divided by C1 times gamma cube plus delta cube. So NITO's argument only works when C2 is equal to C1. But in all other cases, when C2 is not equal to C1, this claim is wrong. So in the paper, we actually demonstrate a counter example over GF2 to the 16. And we also give a equivalent representation of the problem of security of this NPMAC construction. Our second contribution is a relaxation on the security precondition of the general SPMAC design. So basically, the previous result proved that the advantage is q square by 2 to the n, assuming that the masking function tau is a 4-wise independent hash function. In this paper, we have given a new notion of universality called 2-wise AXU. Basically, it is a generalization of the AXU hash function. So along with the usual this probability of A, this is the usual AXU notion. So along with that, we need another joint probability of A and B, and we want that this probability should be less than or equal to epsilon square. So given this notion of two-wise AXU, we have shown that you can actually have the same security bound, assuming that tau is two-wise AXU hash function. So and it's actually quite easy to see that any two-wise AXU hash, any four-wise independent hash function is actually a two-wise AXU. And in the paper, we have actually shown that it's not the case the other way. So you can actually show some two-wise AXU hash functions which are not four-wise independent. So it is kind of a relaxation. And our final contribution is a variant of PMAC called PMAC1 called PMAC2. So in PMAC1, we just have these maskings here. So in what we have observed is that if you take a instead of taking a simple XOR, if you take position-based multiplication by 2, multiplication by the primitive element, then you can actually achieve a better bound in terms of dependence on the length. So we have been able to show that the advantage of, okay, there is a typo here, this should be PMAC2, but so what we have been able to show is that the advantage is q square plus sigma by 2 to the n plus mu, where this mu term is you can like for different restrictions on L, you can get length independence. So if length is less than 2 to the n by 4, then the bound is q over 2 to the n by 2, and this term dominates in this region. And beyond that, we can get sigma over sigma to the 3 by 2 by 2 to the n kind of bound. So just to show a graphical representation. So if you just plot all the dominating terms of the three different constructions, so PMAC and PMAC1, they have dominating term of q square L by 2 to the n. PMAC2 has q over 2 to the n by 2, and PMAC3 is another construction by Naito, which he proposed after we identified this flaw. That achieves q square by 2 to the n bound. So it can you can clearly see that this the green line, the one corresponding to PMAC2, it performs better than the blue one for PMAC and PMAC1 within this range from 2 to the 10 to 2 to the 30 message length. So and this graph is computed for assuming that the advantage or the safety margin that we want is 2 to the minus 10. So in conclusion, in the paper, we have shown a flaw in the proof of security of NPMAC, and we have given a reformulation of its security based on an equivalent problem for binary fields. And so as a consequence of our result, the security proof of NPMAC is still an open problem, and we believe that the proving the security will be at least as hard as proving the tight security of PMAC1. As a second contribution, we have shown a length-independent PRF security bound for SPMAC with a relaxed precondition on the hash function, on the masking function. And as a third contribution, we have given a new construction called PMAC2, which achieves length-independent PRF security bound with some restriction on the length. Thank you.
Thanks, Ashwin. Are there any questions in the audience? Are there any questions online? So I actually have one question. So PMAC2 differs from PMAC1 in the fact that the checksum is replaced. So technically you just set say the like polynomial hashing there in the checksum. Do you think there is another way to fix? I wouldn't say fix, but to make PMAC1 with the powering up approach length independent at a local by a local solution block size instead of doing a polynomial hashing?
Yeah, I mean, even the security of PMAC1 is still not clear. Like, we are still not sure whether it's just Q square L or whether we can improve it to Q square. So, I mean, just proving the security of PMAC1 will be probably another solution, but
okay.
Yeah, I mean.
So you're basically saying that you think it might be possible that PMAC1 is already length independent, but we simply cannot prove it.
Yeah, I mean, proving it will require, I guess, to solve a really hard problem on binary fields, I guess. Like, basically, we have to show something like a 2-wise AXU property on this masking.
Yes. Yes, I see.
With just one hash key, I don't see how we can show that.
Okay, so your suggestion is that we improve our proof skills. Yes, never mind.
Otherwise, yeah, I mean,
yes.
This approach that we have, I guess, that seems to be the most natural way to do that. Okay,
thank you. If there are no other questions, let's thank Ashwin and all the other speakers, and also Tatsu for being online chair. Let's thank everyone again. Then we go for a coffee break, and in half